This section explains the basic architecture of model theory, how syntax and semantics meet across a single bracket. There are two worlds joined by one bracket. On one side sits syntax, a language's formulas, finite strings assembled from relation and function symbols. On the other side sits semantics, the structures, sets that carry interpretations of those symbols. The satisfaction, relation pairs them, and everything the chapter builds is a refinement of that single pairing. A theory is the syntactic shadow of a class of structures. A model is a structure that casts the right shadow. The two directions form a Galois connection, where the closed sets are deductively closed theories on one flank and elementary classes on the other. Elementary equivalence is indistinguishability through this bracket alone, strictly coarser than isomorphism. Predict the rest from here. Every later theorem measures how tightly sentences can pin down a structure. This section explains the one relation that model theory is built on. Model theory rests on a single relation, the satisfaction relation, written as a double turnstile and read as models. It is the bridge from a sentence to the structures that make it true. This bridge is defined by recursion on formula complexity. So a formula is what it does to structures, its meaning assembled compositionally from atomic truth outward. Fix that bridge, and the rest is leverage. A theory is a set of sentences. Its models are the structures on the far side. Elementary equivalence is the indistinguishability that satisfaction induces between structures. IS diorum is the first dividend. Truth in an ultra-product is the ultra-filter's majority. Vote over the factors, proved by that same induction. And majority, truth over a filter, is precisely the machinery that will force compactness. This section explains why first-order logic cannot feel its own scale, which is the whole chapter, and how its three tools each say that one fact once. An elementary extension. Written A is an elementary substructure of B, enlarges a structure while no formula notices the difference. Compactness says, the only obstruction to having a model is a finite one. A theory is satisfiable if and only if each finite fragment is. Leeuwenheim and Skolem then slide any infinite model to every infinite model to every infinite model, to every infinite cardinality, up or down. The generative move is this. Truth is preserved under a relation blind to size, so finitely consistent syntax always materializes into a model, and nothing first order can pin a cardinality. Tarski's test is the local criterion that certifies the elementary substructure relation. Pointwise, satisfiability in B is already reachable inside A. This part explains how an ultrafilter turns a product of structures into one structure, where truth transfers coordinate by coordinate. An ultrafilter is a two-valued measure on an index set. Every subset is decisively large or small, and finite intersections of large sets stay large. Quotient. A product of structures by it, and Wally's theorem falls out. A first-order sentence holds in the ultraproduct exactly when it holds on a large set of coordinates, so truth transfers coordinate-wise. Compactness is the corollary. Index the finite fragments of a finitely satisfiable theory, take an ultrafilter concentrating on ever larger fragments, and one ultraproduct satisfies them all. Local consistency becomes global existence. The elementary extension is the ultrapower's diagonal. A structure sits inside its own copy, preserving every truth, now carrying new elements, like a positive infinitesimal beneath every real. This section explains quantifier elimination. The idea is to strip every there exists, and every for all, from a formula and lose nothing. A theory has quantifier elimination when each formula is provably equivalent to a quantifier-free one. The chapter's entire payload is that this one syntactic collapse is a tameness verdict. Definable sets shrink to Boolean combinations of atomic relations, and truth stops depending on the ambient universe. What an existential formula asserts, if it can hold at all, is already forced by the quantifier-free data that any substructure carries. So a shared substructure, A, decides every sentence with parameters from A, identically in every model extending it. That locality is why the downstream criteria do real work. Robinson's test and substructure, completeness both rest on it. Dense linear orders, algebraically closed fields, and real closed fields all earn their definable geometry precisely here. This section explains what it means for a theory to admit quantifier elimination. A theory admits quantifier elimination when every formula collapses to a Boolean combination of atomic ones, so the quantifiers, there exists, and for all atomic description, the generative move is closure under projection. Project the solution set of a system down a coordinate axis and you land back among the same quantifier-free sets, so no new geometry is ever born from a quantifier. A set's whole complexity is then legible from its atomic description. This is why algebraically closed fields eliminate quantifiers. The projection of a variety stays constructible, Chevalier's theorem wearing logical clothes. The payoff. Types reduced to atomic facts, so an isomorphism of finitely generated substructures already forces elementary equivalence. Model theory becomes algebra. You read straight off the equations. This section explains what a countable model of a complete theory really is, and how a single dial organizes all of them. A countable model of a complete theory is nothing but its pattern of realized types, meaning which complete descriptions of tuples actually occur in it. One dial generates the entire chapter. A type is either isolated and so forced into every model, or it is not. And the omitting types theorem lets you drop it. The extremes name themselves. The atomic, or prime, model realizes only the forced types. It is the smallest, and it embeds into all others. The saturated model realizes everything possible. It is the largest, and it receives all others. Freize's limit is the homogeneous object assembled from an amalgamable class. Vaught's theorem that no complete theory has exactly two countable models then reads off as a lattice fact. The order of realization patterns cannot have exactly 2 points. This section explains how classifying countable models turns into topology on a space of types. A countable model is fixed by which types it realizes, so classifying countable models becomes topology on the type space, written Sn of T. This is a stone space whose points are the complete types. The generative move is isolation. A type is isolated exactly when one formula phi pins it down. That is, when the set of models satisfying phi is a single point, a singleton. This is exercise 4.2.1. Being isolated is the same as being a topologically principal point. Bare category then splits realization from omission. An isolated type appears in every model. A non-isolated type can be omitted, since the omittable types form a meager set. This is exercise 4.2.2. The two poles fall out as extremes. The atomic model, also called the prime model, realizes only isolated types. The countably saturated model realizes all of them. The saturated model exists if and only if the type space Sn of T is countable. This section explains Aleph 1 categorical theories and the theorem that governs them. Categoricity in one uncountable cardinal propagates to all of them. That is Morley's theorem, and this chapter is the machine that forces it. The primitive is this: an uncountably categorical theory admits a single numerical invariant, a dimension, and a model's isomorphism type is a function of that dimension alone. So fixing the cardinality fixes the dimension, and fixing the dimension fixes the model. This is the vector space move. A space over a field is determined up to isomorphism by one cardinal, its dimension. That move is transplanted to arbitrary first-order structures through strongly minimal sets whose algebraic closure carries a pre-geometry. The uncountable caveat is itself the structure. Below Aleph 1, dimension does not yet rigidify the model. And countable categoricity obeys a wholly different law, the counting of types, where dimension plays no part. This section explains why a theory, categorical in one uncountable size, is categorical in all of them. One uncountable model forces all of them. A theory with a unique model of size, Aleph 1, turns out unique at every uncountable cardinal. This is Morley's theorem, and it holds because such a theory admits no free parameter beyond a single dimension. The model is coordinatized like a vector space over a fixed field. Fix the dimension, and you fix the space. Uncountable size selects an uncountable dimension, and dimension alone pins the isomorphism type, so the count of models collapses to 1. The chapter's labor is building that coordinate, total transcendence, Vautian pairs, and a strongly minimal set whose algebraic closure behaves like linear span. Categoricity is dimensional rigidity, and everything downstream is just measuring the dimension. This section explains Morley rank, a notion of dimension without coordinates. A definable set has Morley rank greater than or equal to alpha plus 1 exactly when it splits into infinitely many pairwise, disjoint definable pieces, each still of rank greater than or equal to alpha. The rank is an ordinal that counts how deeply the set keeps fracturing. Rank 0 is finite, consistent, algebraic. Negative infinity is the empty set. The chapter's payoff is that this purely logical recursion on formulas recovers geometry. In an algebraically closed field, the Morley rank of a tuple equals its transcendence degree, which is the Zariski dimension of the set. The generative move is Cantor and Bendixson measure a thing's size by iterated splitting rather than by counting axes. Change what split means, and you get every other ordinal valued rank. This section explains Morley rank, the model theoretic notion of dimension built from branching. A definable set has Morley rank greater than or equal to alpha plus 1 exactly when it splits into infinitely many pairwise disjoint, definable pieces, each still of rank greater than or equal to alpha. Iterate this transfinitely, and you have measured ordinally how much room a set has to keep subdividing. This is the model. Theoretic replacement for algebraic dimension, available wherever the retic replacement for algebraic dimension, available wherever the recursion terminates, that is, in the omega-stable theories. Structurally, this is a Cantor-Bendixson rank on the space of types. A type isolated only at stage alpha is a generic point, one of maximal rank, and the Morley degree counts how many such generics survive. Independence, genericity, the whole geometry of stable theories descend from this single splitting count. Dimension as branching depth, nothing more. This section explains what makes a theory simple. In the model theoretic sense, a theory is simple exactly when forking, the chapter's abstraction of dependence, behaves the way independence should, symmetrically. Read forking as the model. theoretic air of linear independence in vector spaces and algebraic independence in fields. A type forks over A when it commits to more than a forces. The thesis is that on simple theories, this relation earns every axiom you want. Symmetry, local character, meaning forking already happens over some small subset, and the independence theorem, meaning independent conditions amalgamate. So a simple theory is characterized by what its independence does, never by what its models enumerate. Here is the boundary. Simplicity buys a symmetric independence. It does not buy a unique, non-forking extension. That uniqueness is what stability adds next. This section explains why a theory is called simple and what non-forking independence buys you. A theory is simple exactly when the relation does not fork over, behaves like linear independence. Forking is the model theoretic name for dependence. A type forks over A when adjoining parameters forces a genuine constraint, the analog of a vector collapsing into the span of others. The chapter builds one relation, non-forking, written as A is independent from B over A, and shows it satisfies the axioms a dimension. Theory demands symmetry, transitivity, local character, and the independence theorem's amalgamation of independent extensions. Simplicity is the condition under which those axioms hold. The boundary comes next. Stability in Chapter 8 adds stationarity, meaning unique, free extensions, which simple theories generally lack. Forking alone buys you independence without uniqueness. This section explains stability, the frontier where a single syntactic band buys a whole geometry of dependence. A single band does all the work. No formula may linearly order an infinite set. That local combinatorial condition, the absence of the order property, is secretly a definability condition. In a stable theory, every type is itself cut out by a formula, so the structure can name its own types. Definability is what makes non-forking independence symmetric, stationary over models, equipped with canonical bases, a genuine geometry of dependence. The chapter's arc is one equivalence. Few types is equivalent to types definable, which is equivalent to tame independence. Instability is the mirror image. Encode an order, and the type count explodes, and the geometry dissolves. Stability is precisely the frontier, where syntax buys you semantics. This section explains how a single prohibition organizes the whole theory of stability. Stability is one restriction doing all the work. Forbid any formula from ordering an infinite sequence, let no definable linear order hide inside the model, and an entire geometry of independence unfolds for free. The spine of the chapter is that one equivalence. Having no order property is equivalent to having few types, at most the cardinality of the parameter set, A raised to the power of the cardinality of the theory, T over each parameter set. That is equivalent to every type being definable. And that is equivalent to forking yielding a symmetric, transitive independence relation. One that is equivalent to forking yielding a symmetric, transitive independence in a field. Instability is diagnosed by escalation. First the order property, then the independence property or the strict order property, then the tree properties, each a sharper way for a formula to encode complexity. Tameness is the absence of exactly this encoding. Count the types, and you have already decided the geometry. This art explains what a prime extension is and why its existence and uniqueness both rest on a single mechanism. The prime extension is the initial object, the model over A that embeds elementarily over A into every model containing A. It is the smallest completion of a bare set into a world. The purpose of this chapter is its existence and its uniqueness, and both turn on one mechanism, constructibility which builds the Model 1 mechanism, constructibility, which builds the Model 1 a chain of isolated types. Existence holds when the theory is tame, meaning totally transcendental or countable and stable. Uniqueness is res-A result. Any two constructible prime extensions are isomorphic over A. The sole obstruction is indiscernibles, and stability diffuses it. Every infinite indiscernible sequence is a Morley sequence, so an atomic extension carrying no uncountable set of that kind is precisely a prime one. This section explains how a stationary type is pinned down by its Morley sequences. A stationary type remembers nothing beyond what its Morley sequences agree on, and what they agree on is exactly the average type, the formulas holding for all but finitely many elements of the sequence. Two Morley sequences are parallel precisely when their averages coincide, which is precisely when they name the same global non-forking extension. So parallelism and equivalence on sequences collapses onto equality of one canonical object. The sequence is an avatar, and the non-forking extension is the invariant it points at. A shared tail. J witnesses the collapse. The average of I0 equals the average of I0 followed by J, which equals the average of I1 followed by J, which equals the average of I1. The type is known entirely by what its indiscernible witnesses concur on, and nothing else survives. This section explains the fine structure of Aleph 1, categorical theories. One dimension governs everything. And Aleph 1, categorical theory hides no genuine multiplicity. Every model is coordinatized over a single, strongly minimal set, whose algebraic closure is a pre-geometry, a matroid carrying an honest notion of dimension. The chapter's labor is to show that the whole model is algebraic over that core, built up layer by layer, so its isomorphism type is pinned by one cardinal, the dimension. A global statement that all models of a fixed uncountable size coincide, thereby collapses to a local geometric fact that one definable set carries a dimension theory and everything else is forced over it. Uncountable categoricity is the opposite of richness. It is structural poverty. The fine structure is the anatomy of a theory with exactly 1 degree of freedom. This part explains how an uncountably categorical theory reduces to a single geometry. An Aleph 1 categorical theory conceals a single, strongly minimal set, and the combinatorial geometry of that set governs the whole theory. That geometry is algebraic closure read as a pre-geometry, a matroid. Every model is almost strongly minimal, coordinatized over that one set. So a lone cardinal, its dimension, fixes the model up to isomorphism. The fine structure is the anatomy of the geometry, whether closure is locally modular, meaning linear and group-shaped, or not. This is the cleavage Zilber pressed toward. The chapter's work in the book's arc is this reduction. An uncountable classification problem collapses to one geometry and one dimension. Predict the next case by asking what its closure operator forgets.